Hi, so this tutorial is about doing an FSI simulation. So I will do the most simplistic FSI simulation I can think of, and this is a one-way FSI simulation. So you can think of it like so we'll get the result from the Fluent, and those CFD results we will use that to interpolate to the structural analysis solver to see the deformation and the motion of the solid structure. Okay, so this is a one-way FSI simulation. So if you can simplify your problem uh, uh, to uh, to a one-way FSI, it's recommended instead of a two-way, because two-way is more complicated because of the dynamic mesh and the other options. Okay, so let's get started. So I'll just start the geometry. I think I already opened it. Okay, so I'll just randomly create a very simple geometry. Let's see. Sketching rectangle. I'm gonna create a pretty simple geometry in here. Okay, and I'll create one, maybe two, or maybe I'll do two over here. Let's see. Oh, not this one. Let's use line, vertical. Okay. Try to make it a little bit thinner so that actually deformation happens. Same old, you see, I'm not following any dimension or anything. I'm just randomly creating one. So, but in your problem, you can definitely follow up with like whatever type of one-way simulation you want to do. Let's see if it works. Trim, where's trim? There you go. So I'm gonna trim this one, trim that one. Okay, so this would be actually my fluid surface. I'm gonna create a surface from this one. Surface from sketches, sketch one, generate, and I'm gonna go to extrude. I'm gonna do a 3D geometry from this, and direction vector, just normal to this one. So it would be like this, maybe 0.2 meter direction. Okay, didn't press apply, so this would be like this, very small thickness. And actually, let's actually reduce it to 0.1. Okay, and generate. So this is our fluid body, and for solid, so these slots would be our solid, let's say two sticks, like sticking out. Okay, so we will introduce a flow along this direction, positive x direction, and we will see the deformations of these two solid structures. So I need to have a solid body because I already only have the fluid body, so we can rename it actually fluid body, just so that we don't get confused. Surface body we don't need, we can actually suppress it. Fluid body, so we'll just use a fill feature by cavity, yes. Which surface? So I'll just select the surfaces. So that should create two solid bodies over here. So let's click generate. So I have one solid body in here and another solid body in here. Okay, so we have everything. I'm not gonna make connections like creating one part from all these bodies because we're gonna do a FSI simulation from CFD data will be transferred to the solid and then we'll do the solution. So let's see how we can do that. One last thing is let's change it to fluid. These two would be solid. Alright, we're all set with the geometric analysis. Let's close it. Workbench, mesh. So as you can see, I'm just working it out as I would do a CFD with Fluent Solver up to this point. So I'll go all the way through the solution and then I'll introduce the structure analysis part. Okay, so this is the meshing part. It's taking a while. All right, so we're interested in the CFD part, so I'm gonna only consider the fluid body, not the solid body. So I'm gonna suppress both of them in here, and let's create a generalized mesh. Let's take a look. Okay, doesn't look good. 733, so maybe I'll do 100. I don't know. Maybe that would be good. And let's apply an inflation on the boundaries. So, okay. Click apply. Just gonna go with this. Let's take a look. How does it look like? Very unstructured mesh. Again, this is just an introductory simulation, so I'm not very concerned about the accuracy of the mesh. Just to show you the method of how to set it up, like a working one-way FSI simulation. So maybe I'll just stick with this one and let's see if it causes any problem in the future or not. Okay, so after that, which one is our inlet? So let's say this is our inlet. This is our outlet. And let's say this is our top wall. Bottom wall. Let's say these are walls. Okay. And let's say these two are side walls. I'm specifying these two differently because I just don't want to have the no slip condition affecting the flow. So I'm gonna just apply a zero shear condition over there. Okay, so let's say side walls. Okay, and what I really need is these surfaces. So this one and this two. Okay, and the position where we applied our inflation on. So this would be the coupling surface. Okay, so let's call it transfer. Let's say. or maybe just solid. Okay, solid surface. Okay. Okay, so we're done. I think inlet, outlet, walls, side walls, and the solids. Okay, I think we're pretty much done, so I'm gonna update it. Okay, update it. Going to the setup and use the double precision. I'm just gonna go with 8 processors. Hopefully it will not slow it down. Sometimes specifying large number of processors increases the latency time. So it doesn't matter if you just increase the parallel processor and it will increase the simulation, like decrease the simulation time. It doesn't happen always. So there is always an optimum number of cores you need for depending on your number of elements and the solver you select. So use an efficient parallel number of processors. Okay, so this is our mesh, zero geometry. We're gonna do transient flow. Gravity you can apply, but I don't think this would be much important in this case. So I'm just gonna skip that. I'm just gonna check for negative volume, so you have none. Models, I'm expecting turbulence, so I'm just gonna stick with the K omega model, but you can use other models. Maybe laminar model will work as well in this case. I'm not sure. Let's actually try a laminar model. Okay. And materials. So instead of air, let's use a little bit heavier material like water. Okay, it is imported. Solvent condition, fluid body. Let's make sure our water is being used. And if you want to be 100% sure, which I usually do, I always delete the non-used material because I might have missed something, and make sure that I didn't miss anything with the material. Boundary condition. Let's say the inlet is a velocity inlet, and maybe 0.5 meter per second. Okay. Outlet. All right. Okay. The sidewalls. I don't need any shear, so I'm gonna say a specified shear of 0. So no slip condition would be void. And outlet is in pressure play. Everything default is fine. We don't need to change anything. We don't need the dynamic mesh for one-way FSI. Methods, we're just gonna stick with the default features and everything. Monitors, for faster convergence, I'm just gonna stick with 10 to the minus 3. And let's do initialize. We can do a hybrid initialization. Okay, and calculation activities. So we have to save the CFD part of it. So let's save it in each 3 time step, and let's say 0.001 is our time step size, and let's do a half-second simulation, which would be 500. Okay. Iteration, let's increase it a little bit, 40, and all right, you are all set. So let's calculate, and after I finish this one, finishing this one, I'll come back and let's see what we can do about the coupling part. All right, solution is done. Let's take a look at the results. This is an optional option. I just want to take a look at the because I randomly selected the geometry and the boundary conditions. So I just want to take a look at like how this velocity control plot looks like. And as you can see, it has been saved. So these are the timestamps saved for up to 0.5 second. And I'm going to create a plane at in the middle of it. I think this should be somewhere in the middle. Okay, slice it. So this is our plane, and I want to have the velocity control plot. Location is plane 1. Velocity maybe 25 something. Let's take a look. How does it look like? Well, there is certainly some high velocity in here, and as you can see, the solid part didn't move at all. So this is the velocity contour plot we have. So what we're going to do is after 5.5 seconds, like you can check other velocity options. So this pressure and velocity and everything, all the parameters, we'll use that, we'll interpolate that to the structure analysis solver, and we will see the deformation of the solid bodies. Okay, so that's how one-way FSI works. No dynamic mesh, not too much complication, and the application I think I can think of is here you can use a static structure. So the application I can think of it is a lot. For example, if you're designing a airfoil, let's say, okay, so you can check depending on the flow how much deflection or stress developed or deviation of the maybe at the end part of the airfoil, like how does it change. You can see all of those things. Now we need to for the coupling part, just left click and hold, and then connect it with the static structural geometry. Okay, oops, what happened? Okay, there you go. I think I double clicked it, and from the solution, so we're going to use the CFD solution for the setup, the solver part in the static structure. So these two needs to be linked, and then in the engineering data you can edit it to add materials to it. Okay, still we can go back in the project, but this is the engineering data. Now by default structural steel is added as a material, but let's say we want to add some softer material. So you can either click in here, engineering data source, or you can right click in here, engineering data sources, and click on the general materials. So this should give you a couple of materials. As you can see, static structure is added, so that's why this sign is. Let's say we want to maybe polyethylene. This is a softer material, or just in case, I don't know, maybe I'll just add aluminum alloy as well. I'm not going to use that maybe, but if there's too much deflection with the polyethylene, we're going to use the aluminum alloy to see how does the deflection looks like. So here, this is how you can add the materials. After that, let's go back to the project, and geometry is linked, so we don't need to do anything. We need to model it. Let's see. All right, it sometimes takes a while to load. Again, like regular CFD solver and FSI is different in computational time. It takes almost about twice the time because you're doing coupling. But one-way FSI is way faster. Okay, so let's see the geometry. We don't need the fluid body for the structural analysis, so I'm going to suppress the fluid body. We're going to have both solid bodies in here. So what I'm going to do is I'm going to select both solid bodies and assignment material. So I'm going to change the material. Okay, click over here, water liquid static structure. There you go, my solids. So I'm going to use the polyethylene, so I think that would give me the most deflection. So you'll see the difference. Materials is done, and coordinate system connection. So we need to do the mesh. You can generate the default mesh and take a look. Let's see. Okay, doesn't look too much good, but anyways, I guess this is, we can apply a insert sizing and select geometry. Okay, both body sizing maybe. I'm just gonna try to do it as fast as possible. 150, so maybe I'll do the same as I did for the safety part. Okay, 100. Generate, let's take a look. Not much good. Maybe I'll just reduce it a little bit. 50. And let's do another thing, sizing. So it's just going to deviate along this direction. So, okay, fine, this works. I don't actually need this. I'm just gonna delete it. Generate. Okay, and maybe I'll just do this. It's sizing animate. Divisions. Oops, sorry, I forgot to press the control. 2, 3, 4. Okay, so 8 edges, and I'm gonna say number of divisions is just 1, and generate the mesh again. Again, do the meshing if it is important in your case. Okay, this should be fine. The first thing we need to fix is in the static structure, right click and insert. And insert, let's say I want to couple it with the pressure. So I'm going to get the pressure imported from the CFD simulation and apply it on these solid structures to see the changes. Okay, so there should be, okay, let's do this one, fix support first. Okay, the other one is in the imported load. Okay, imported load is like how do you want to, we want to import the load like the pressure or some other loads. Okay, and the fixed support is well, these solid structures, where is it fixed? So I'm gonna select, let's say this is at the top part of the geometry, so I'm gonna say this top part of this one and the bottom part of this one, these two would be fixed. Okay, click apply. Two faces are fixed. And in the imported load, right click in here, insert, so body temperature or pressure. So I'm gonna load pressure in here. And how do I want to couple? In the geometry, like where do you want to, like which surface do you want to couple it with CFD pressure? Okay, so I'm gonna select this surface because these two sides are connected to the walls, so it doesn't matter much. So I'm just gonna select that side surfaces and couple those pressure to see the changes in the solid bodies. Okay, the top and the bottom of this one is fixed, so we don't need that. So we have 6 faces, and the program control source time, you can range it. Okay, so minimum time is 0, maximum time is, in our case, 0.5. Make sure you don't exceed the time you did the simulation in the Fluent. Okay, so that gives you a list. You can even modify it in here, I think. After that, active row. Transfer definition. Transfer definition is like which surface are you going to couple it with? Also, I'm gonna use this surface. So remember, we selected the solids for the same surfaces while we are setting up the Fluent solver. So we're gonna select the solid from the CFD surface, coupling it with the surface we have selected in this option. Okay. It takes a while to load. I've already clicked it, it's just stuck. So let's wait until it updates. Yeah, there you go. Solid. Okay. And after that, the rest of the part is not that important. So just for the running case. So what you can do is right click. You can do import load, or okay, I'm gonna add some solution. So I want to see the total deformation, and let's say I want to see the boneless stress. Okay, and right click on the solution and click on solve. So that should start coupling. So as you can see, it's 7%, and what I noticed is it immediately jumps from 7% to almost 100%. So you just have to be patient for a while to let it finish. Okay? Don't think it crashed or anything, just wait for a while and it would be done. Okay, after that we'll see the total deformation and the stress acting on these surfaces from the fluid flow. Well, it is updating quite fast. That's great. I guess this was the number of elements was really low, so that actually helps. So this is the total deformation after the 0.5 second. Let's see, maybe this one will help. Okay, so let's go play it. So this is, you see, this is due to the fluid flow after the pressure coupling. This is how the deformation on the solid body of the material polyethylene is acting up. You can make it slower by maybe using 4 seconds. It slows down. It actually like showing the 0.5 second simulation in 4 seconds. You can slow it down by 10 seconds. You can make it really fast by this one. So this is how you can set up a one-way FSI. You can take a look at the stresses developed. Okay. Okay, stress is developed, and you can do a lot of more things. So this is the most simplest approach to run an FSI, one-way FSI. You cannot transfer data from the deflection, like the static structure, towards the fluent flow. This is the one way. So you'll get the CFD results first, and you'll use that interpolated result in the static structure to get the deformation. Okay, so this is called a one-way FSI. Thank you.